Greetings once again. This is Timur. Thank you for your interest on exabyte.io. Today we'll be speaking about getting started with the platform. And before we start this presentation, a couple of important points. The goal of this webinar is to help users understand the main concepts behind the platform. And this is the first webinar in a monthly recurring series where we first Friday of the month speak about getting started, and then third Friday of the month we'll speak about advanced topics. Every participant by now should be a registered platform user. Every participant will receive this presentation in a PDF format, so no need to take the notes. And highlighted text in this presentation contains a link to your web page, usually to the documentation online. We will also record this presentation and make it available online so that you can follow the explanation on your own. If you have any questions at any point during this webinar, please feel free to ask either using the Q&A option of the Zoom panel or the chat option. We will go through the questions during the dedicated spots and at the end. So the agenda for today is like this. We will first speak about the Exabyte platform and its capabilities, the vision, the mission of the platform, the current capabilities. And then we will dive a little deeper into the core parts. We will speak about what is under the hood, what are the common user interface components, and a little bit about the accounts and service levels. And then we will proceed to speak about each individual entities in more details. We'll talk about how we can upload, create new materials, search through them, and design them, assemble them in 3D. And then we will speak about the simulation workflows, the logic that we employ in organizing this information. And we'll finish with speaking about how we can run and view the simulations. Okay, so let's start with the Exabyte platform. And if you think about how the R&D landscape evolved over the last 10, 20 years in particular, we'll see that there's a new paradigm, the data-driven science paradigm, where we don't just rely on experiments, theory, or single computation, but we rely on aggregating the data that comes from these first three domains, and then applying artificial intelligence and machine learning on top of this data. And this transition that happened relatively recently requires a new kind of digital approach, an approach where we can organize the data, where we can prepare it so that artificial intelligence can be applied. And that's exactly what we solve as a fundamental problem with the Exabyte platform. And how do we approach it? We approach it by focusing first on a central point, a point that can connect multiple different types of sciences, computational sciences, experimental sciences, data sciences, as well as the IT administration and management, so that they all can exchange their insights, they all can work together, and the focal point for it is the cloud. Not necessarily the public cloud like Amazon Web Services, but a focal point where all these people can exchange information. And then in order for this to be impactful, we have to support a toolchain of different simulation tools. That could be either in-house, commercial, or open source. And all these tools have to feed into a data platform that aggregates the results and predictions that they make in order for us to be able to run machine learning. And of course, last but not least, all of this has to be secure so that no intellectual property leaks when we work on something like this within an enterprise organization. So that's exactly how we see the future. And in order to realize something like that, we have a multi-tiered approach. First, we focus on maintaining a set of open source components that together form the foundation for a fair R&D ecosystem. And the term fair stands for findable, accessible, interoperable, reusable. And we start with data standards. standards that define the core entities that the platform operates with, such as material structures, simulation workflows, calculation jobs, and materials properties. All are implemented as data structures and JSON schema data structures to be able to very well clarify how we can store the information about each one. And then we provide extractors to convert the data from other existing sources into the exabyte format. As we call it SC here, exabyte source of schema as an example, so brevity. We have an example for an extractor on GitHub, and we have standards also deployed as an open source repository there. And finally, we also have a set of applications that are built using extractors and the standards inside themselves, so that users can do fundamental capabilities like designing material structures or source and organize the workflows information. We start with the most well-known use case to us for computational scientists, where they can be using a familiar simulations tool. And then through an extractor, we organize the data coming out of this tool and store it inside our database, so that other users within the organization can either access the results or collaborate with them without necessarily knowing in details what this particular tool does, but instead by adopting the standardized, the organized approach of our platform. So the public part of it today is available online at pw.x. And some of these components can be also licensed and further deployed in the private scenario so that security concerns are resolved. We also have support for the data scientist toolchain as of today, and we have plans to incorporate experimental data so that experimental scientists can at least exchange feedback with their computational colleagues, or they can also introduce external elements such as either high-performance computing clusters that they run externally, laboratory equipment that can be digitized, and any kind of data platform tools that they have outside of exabyte platform. So this completes the picture and how we think about the ecosystem and its development. Now, if you think about the digital materials R&D in particular, we will see that there are important components that constitute this life cycle. First, we design material structures, then we design modeling workflows, and we provision the infrastructure for the workflows. We have to control and assert the completion of these calculations and collect the data that they produce, build analytics, and finally do some experimental validation. And today, our platform supports points 1 through 6, and 7 is also in development. So here's an example page that demonstrates how an account looks like inside the platform. We see that there are many entities that we store inside the account, like materials, workflows, and jobs. And there are people that are members of this account that can collaborate on editing, creating this information together. So the step number 1 is when we design the structures, such as this surface component, for example, for aluminum gallium arsenide. And as we can see, we can cleave it at a particular angle, and then we can store it under a certain tag so that we can faster find it in the future. This could also be a set of structures organized into a material set. So in this case, I'm looking at an NAB, matched elastic band set, that specifies a particular reaction. Here we have an atom of hydrogen migrating along a specific path inside the larger matrix. And that's how we code in the chemical reaction from initial to its final step. Now, once we have the materials, we need to apply a certain workflow to extract a particular property of this material. And we have a set of template workflows as well as the capability to design new ones organized within the exabyte platform. So we can apply a workflow that will calculate the electronic band structure. after we have designed a material. And then we can set up its computational parameters in the platform as well, such as which cloud provider it will be running on, and how many cores, how many nodes and such. Then we can submit this calculation for execution from the cloud, from online platform, and then see how it progresses, make sure that it actually progresses in the right direction. And in the end, at the end, we can get the result. So these are the basic steps for the band structure and for the elastic band calculation for the chemical reaction profile. For people who do this on a daily basis, we have the capability to deploy something like Python or command line tools to be able to automate all of these actions. So here's an example script where we import materials from materials project from an online database, and then we can create calculations for each of these materials and subsequently wait for these calculations to complete. So as you can see, materials are created. One script is executed, for each of them a calculation is created, and then we wait for these calculations to complete and extract the data that is produced in each of these calculations to assemble a data frame that can be further used to build some machine learning approaches. Okay, so programmatic functionality, access to RESTful API is a possibility. And when we work with RESTful API with Python, it is convenient to use Jupyter notebooks, which we support natively as well. So we can do things like set up our communication with the RESTful API through authentication parameters, and then retrieve the information stored in our account programmatic, like a list of materials. Here are the applications that we support today. It includes a set of modeling applications on a potential density functional theory level, a local orbital density functional theory, and molecular dynamics. And a set of analysis tools like VMD, XCrystal, and such. We also support scripting applications, so Python and Shell through command line usage, so users can install packages that they're interested in. And that can be done by accessing the platform through command line. So we use modules environment, and this is how we provide information about the modules that are globally supported. And then users, after that, can install the software that they like within this environment. Here's a quick example. So when we inside the platform, we can open the right-hand sidebar, click on the terminal, and access the command line environment right there, edit the batch script, submit it, and get the result. Okay, so let's summarize midway about the core points of the exabyte platform. exabyte.io is a comprehensive ecosystem for materials and chemicals research and development. And the main goal of this ecosystem is to transition today's fragmented, siloed approach to a findable, accessible, interoperable, reusable infrastructure to prepare it for the data-driven, artificial intelligence-driven science in the future. And our goal is to supercharge computational scientists by providing them with a dedicated environment to organize and accelerate their work. And the platform today can be accessed on multiple levels through the web interface and alternatively through programmatic means like RESTful API and command line. Okay, so now let's understand what's under the hood. If you look at our GitHub page, the GitHub page for exabyte.io, we can see some of the implementations of the components that I was just explaining from this diagram. So standard is implemented inside SE repository. Extractors, we have an example for inside exaparser. An example application is a materials designer, and RESTful API examples, we also have those as part of the open source repositories in our webpage. Really, it is important for for us to identify the entities in order to organize the information and do it efficiently. Because of the complexity and diversity of material science, we really have to solve this problem first before we can incorporate in a modular way a diverse set of simulations and experimental data. And that's why we identify the main entities and concepts that the platform works with, such as material structures, simulation workflows, and we separate those on purpose because some simulation engines, for example, hold this information together, which makes it extremely difficult to store it, and there could be a confusion. Once we have material and workflow together, we can run a simulation job, and a job itself also includes compute parameters and some compute platform information as well. The way that we define the data structures is explained inside SE repository, exabyte sorts of schemas and examples. They are organized into JSON schemas and open to public. And as a bonus, this repository is also both a Python pip package and a JavaScript NPM package, so that users can utilize it inside their projects, both in JavaScript and Python, to validate the schemas, to validate the data structures that they use. So here's an example schema. This is how we define a material. It contains a formula, unit cell formula, basis, crystal basis, crystal lattice, a set of derived properties, and a bunch more keys. And here is an example representation of a material adhering to this formula. In this case, it's silicon FCC. We have atoms at certain positions, certain kind, and a set of derived properties inside this data structure. Now, why is it important to understand this data structure? Sometimes there's a set of functionality that we want to access either through RESTful API or through some additional platform capabilities, like expanding the actual data structures that we show inside the user interface. For that, to understand what's stored, the information about the schemas is helpful. Okay, so every entity that the user encounters in the platform is defined inside the exabyte data convention. These definitions are meant as a unified format to incorporate data from multiple different material types and modeling approaches. And the platform provides a user interface to work with these entities and alternative access means. We do welcome contributions, so anybody can fork the open repository on GitHub and put a pull request. Here is an example for Materials Designer, where we have been implementing additional features with our colleagues from Japan. And next, let's talk a little bit about the user interface as it is seen to the users once they log in. So here are the basic components of the main user interface. We have the header at the top, we have the left-hand sidebar and the right-hand sidebar, footer, and support widget. And usually at the very beginning, the most important one is the support widget to be able to ask questions. And that's how it looks when extended. And we strongly encourage users to put a screenshot, or even better, a screencast of the problem they experience so that we can understand it better. There is also an interactive chat on the right, in the bottom right corner. And this is meant to help people sign up, to help them during the registration process. So we discourage its use after sign up for registered logged in users. Now let's speak about the left-hand sidebar. Moment. To open the left-hand sidebar, we need to click over here into the top right corner. And as you can see, it contains short links, links to jobs, materials, workflows, the entity. In the right-hand sidebar, we have things like the web terminal, access to the payments and billing information. And beyond that, we also have three main entity-related interface components. So for each of the entity types, for materials, workflows, and jobs, we have three of these kinds of user interface components. An explorer, or a list listing all the entries, a designer, and online development environment for the creation and editing of the entities, and a viewer. So a dedicated page that can allow us to visualize one or more entities without necessarily editing them. Okay, so here is an example explorer for materials. You can see that there is a list of them, and there is a set of actions. So actions that can be grouped and act on multiple entries are at the top. And then per each of the entries, we have a set of specific actions to it. At the top, we also have a search bar so we can filter the entries in the list. Now, here's an example designer, materials designer in this case. And as you can see, it also contains multiple subcomponents like a header menu, the list of items that are currently active inside the designer, a crystallographic panel, and 3D interactive viewer. Yeah, materials designer is also a standalone JavaScript application, so that developers developing new applications for material science can use it as a dependency. And here is how a viewer looks like. We can visualize material information and adjust some metadata about it, such as add tags or change the name, for example. Okay. Now, regarding the accounts in the platform, accounts are the concepts, the entities in the platform that can perform actions on materials, workflows, and jobs. So accounts define different ways of how users can interact with the platform, and accounts have members or users themselves. There are organizational, team, and personal accounts. Personal accounts can only have a single member inside them, the person, the user themselves. And organizational team accounts can have multiple types of members with different kinds of permissions. And account members for the team account have shared access to the entities that they own as set up by account administrators. It's also important to understand the concept of the entity collection and the entity bank. So when we create new accounts, we initiate them with a single material and a single workflow. And for each account, this material and workflow are the same. So in order to avoid duplication and understand how many unique materials we have introduced the concept of entity bank. Entity bank contains unique copies of materials and unique copies of workflows. So when there's an account for which the private data access scenario is enabled, which is a premium feature in a platform, no other accounts can access the materials bank entities that are created from this account entities. And vice versa, when this account has public data access right, other accounts can see what they produce inside the bank. So that's a way for us to first identify unique entities and then securely share them between different accounts. Now, we recommend that users start with importing some of the curated workflows inside the bank when they first enter the platform. And for that, we can navigate to materials bank by using this option, import from bank option in the toolchain. The entities that are produced by a curator's account are those that we control. They come from Exabyte team. And those usually are high quality, at least initially, and guarantee that they will work and the calculations won't fail. Now, the way that a set of options that are available to the account is governed is through the service levels. Service levels define the features that are available to accounts. And we have four basic service level types. When users just create the account, they are on a free service level. They can access the platform and they can utilize the trial credits to try the paid functionality. And then if they decide to proceed beyond that, they can subscribe for a pro or individual account service level. To be able to collaborate, we have the team service level, and for larger teams, for enterprise customers, we have enterprise service level. Some of the features that are available to this different service levels include things like the amount of disk space, availability of private data that I just explained with the entity bank scenario, the account member numbers, support severity, and things like that. So under the hood in the platform, we have the data standards that define the entities, the concepts that we work with. And the platform really provides a user interface, an interface to work with these entities. There are multiple different connection types. The accounts can perform actions on the entities in a shared access way, allowing users to collaborate. And the features that are available to accounts are defined through service levels from free to enterprise. Okay, I reached my first Q&A break. Let's see if you have any questions. I don't see any questions as of right now. Just gonna check the chat. Okay, no questions as of right now, so let's continue on and speak more in details about materials. So usually that's the first entities that our platform users start with, and usually the first action that they execute is to upload materials information that they have stored on disk on their laptops, on their computers. And to do that, we will need to navigate to the list of materials of the account, and then select the upload action at the top. It will open the upload dialog, and then within the upload dialog, we can select items. So in this case, I'm selecting multiple postcard files. So they are now available for me inside this dialog. And I can preview and make sure that these are actually the files that I want to upload there. And then I can select one of them and attach metadata to it. So I can add 2 tags to this entry so that when the material entry is created, it will have the corresponding tags, right? And then I can select multiple entries inside this dialog and click upload, wait for a few seconds, and then see this green message saying that the upload was successful. And when I come back to my materials list, I can see the new entries created there. So new entities corresponding to the files that I just uploaded, and one of them has the tags just as expected. And as you can see, through a materials bank, we also have identified that one of these materials, in fact, was previously uploaded by the user, and we also have calculated its bank gap before. Okay, so this is a way for new users to save some time and reuse the previous information without duplicating. The second option is to import structural information from an online database, and today we support Materials Project as the structural database provider. To do that, we need to click on the import button in the toolchain above and search for the material by its formula. So I'm searching for magnesium oxide and a couple of entries. I'm selecting one of them according to my preference and click import at the top. Wait for the success message to be shown. And again, I see this material at the top of the list here. Okay, we keep the tags, the original tags that came from Materials Project, keep the original information, and when we expand this entry, we can also see the original information that is retained. Okay. The third option is to copy materials information from Materials Bank. As I explained, the more users are joining our platform, the more information we have inside the bank entities, the bank collections. So we can navigate to the bank page by clicking on the left-hand sidebar and then bank and then materials. And just like in the previous example, we can search for a particular material by formula, select it and click copy, which will copy the entity into our account collection. Okay, when we navigate back to materials for this account, we can see the newly imported material at the top. There is a shortcut, import from bank, that will take you right into the materials bank collection to be able to copy from. Now, in some cases, we want to search for more than just a formula. And for that, we have implemented this advanced search option, which is this second option in the list. And with this option, we can build a query. So there are certain fields that we support and a set of logical rules that can be tying up those fields together to create a query. So in this case, I'll be searching for a material that contains aluminum in its formula and that has the unit cell volume less than 80 angstrom cubed. Angstrom cubed is what we count the unit cell volume in, and also contains high pressure as one of the types. Okay, so this narrows down the list to just one material. And if I reset the filter at the top, click reset, I can go back to the full list. All right, that's how the advanced search works. And last in this section, let's speak about how we can design, create new materials from scratch. And for that, we have implemented the materials designer component, which is at the same time also a JavaScript application, open source, to utilize and start a session with materials designer. We can click on this plus button. And here is how it looks like. We will be presented with a page that contains multiple different components. And I will demonstrate a basic usage scenario for this component. So at the top in the header, we have menu items that we can open to invoke certain actions. Excuse me. So if you click on the input output menu at the top, we see that there are certain options available there. Let's click on the import and select one of the materials that we have inside our collection. So here we present the user with materials that already have been imported, uploaded, or copied from bank and are part of their collection. So here we would search for aluminum, for example, and then import it. And you can see that we pre-initiate materials designer session with the default material, silicon FCC in this case, and then the second material is being added into the list. So we can switch between the two, and we can delete the first one from the materials designer session. So this deletion doesn't delete this material from database, it only removes it from this online session. All right, and this is how we can focus on designing, adjusting this material structure as necessary. So some of the options here, we can produce things like supercells, surfaces, meshed elastic band sets, interpolated sets, and just edit and replace some of its atomic information either here inside the crystal basis dialog, or we can dive deeper and open the 3D designer and adjust the positions per each atom or modify atoms as a group inside that session. This is a topic for the advanced webinar, and I'll omit it for that. Okay, now let's continue and speak about the second type of entities, simulation workflows. And just like with materials, there is an option to copy or import workflows from bank. And that's what we would recommend as the first option. So when users just create an account, we recommend going to the workflows bank by navigating to it through the left-hand sidebar and searching for the desired properties. For example, if I want to extract band structure, I would search for it, select the corresponding workflow, and we also demonstrate which application engines are used inside this workflow, like Quantum Espresso and what version. And I can click copy to copy that workflow into my account. And then after it's there, I can open this workflow inside the workflow designer to edit it. But in order to understand how to edit the workflows, we first have to speak a little bit about the inner structure that we employ inside the workflows and how we store the information. We organize the information inside the workflow into sub-workflows. So subsets that contain specific logic that is unique to a single simulation engine and a single model and method. A model in this case could be something like density function theory, and a method could be set potential or local orbitals or particular computational implementation of the model. And then within each sub-workflow, we can have a set of units which are elemental computations that on purpose are introduced to be able to reuse some of this computational logic. A unit is the smallest indivisible type of computation, right? So we can't consider anything smaller than that. And units can have different types. For example, if you run Quantum Espresso, it will be an execution type unit. And if you do an assignment of a variable, it will be an assignment type unit. If it's a condition that splits the flow of the workflow, it's a condition unit. And then execution units can have different executables associated with it and different kind of flavors. So for self-consistent field workflow for pw.x in Quantum Espresso suite, we'll have the corresponding flavor. For non-self-consistent field, for band structure calculation, we can have the corresponding flavors again to make each of these templates to be reusable between multiple different sub-workflows. Now, when we open the workflow designer, it also presents us with the header menu, the items list sidebar on the left, and sub-workflow editor panel. And now I'm going to demonstrate how we can add or delete sub-workflows. So for that, we're going to need to click on the plus button, and we can see that we'll be appending to the current existing sub-workflow. So this is how we add a sub-workflow into the list. Clicking plus button and clicking apply. Then we can switch between these two sub-workflows, and we can delete one. Now inside the sub-workflow editor, we can adjust the information about the simulation engine and the model parameters used inside the sub-workflow. And we also have the units flowchart, the flowchart of how the units inside this sub-workflow are connected. And if you look deeper into it, we'll see that each of the boxes representing individual units, they have the type, which is shown by the letter in the bottom left corner. And there's a certain logical progression between these units. The currently active one is highlighted in gray, so we can open it if we click on that unit. But in order to understand how it's implemented today, we have to look at the actual logic involved inside this flowchart. And the logic that is involved in the flowchart on the right is actually equivalent to this convergence workflow demonstrated on the left, where we first define, let's say, the initial key point number and an arbitrary temporary variable. And then we run a pw.x calculation and check the output for its total energy, for example, and see whether we have converged the total energy value with respect to the key point grid. So this is an example workflow that implements exactly that. As you can see, it has assignment type units, condition type units, and execution type units. Now, if we navigate further into one of these units, we'll see that it has multiple additional information stored inside itself, such as the application section that contains information about the executable type and flavor, a set of properties that we extract during this calculation. So we have on the back end, we have the functionality to extract some of these properties. Properties are defined in SE. Again, the Python package that extracts these properties is also an open source component. Here we just indicate which properties we actually want to extract. And then the same thing is happening for monitors. Monitors are being extracted during the calculation. So we can see the standard output and the convergence. And the properties are extracted at the end of the calculation as a result. We also can see how this unit is connected to other units within the workflow. And at the bottom, we can see the input file templates. So if we focus on that, we'll see that there is the certain type of templating language that we use instead of plain text inside the input templates. And these templates are populated based on the information from a material, right, and workflow. So workflows and materials have a set of properties that form this template data, and then they're passed to the template to render. And if you look at the preview button, we'll see that inside the workflow designer, we use the default material to render and demonstrate to the user how the rendered template would look like. If we compare the two, we can see that there is a set of template variables that are explicitly rendered inside the preview tab. Now, this is the first render that happens on the web before we submit this calculation for execution. There is also a second render that, as you can see, there are certain variables that are not resolved yet inside the template. And that's because for user, it really shouldn't matter which job working directory this calculation is going to run on the cluster. And we decide that on the infrastructure side during the second runtime render. Why we need the second one? The second render is necessary to facilitate things like convergence and iterations so that the context of the workflow can be changed during the runtime. Okay. Now, once we have the workflow and materials information arranged, once we have the entities created, we can proceed to create simulation jobs. And before we start with that, we need to make sure that we have uploaded created materials and workflows. And we need to make sure that we have enough balance to perform the calculations and enough disk space, storage quota. All of this information is available from the web interface. You click on the right-hand sidebar. And then we need to navigate to the desired project, which is how we organize simulations. Usually people work on specific projects that contain multiple jobs inside itself. Alternatively, if we want to use the default project, we can create the job, so the create job shortcut in the left-hand sidebar. If we do that, we will navigate to the jobs designer. And that's how it looks like to the user. It contains the header menu at the top and 3 tabs for materials, workflows, and computational parameters. So let me demonstrate how we can select the material inside the job designer. We need to click on the dropdown in the header and click on select materials as an option. We are then presented with a list of materials that belong to our account. And then we can select one or multiple materials from the list, which is what I'm doing here. I'm selecting 6 materials, clicking select items, and 6 materials are now present inside this job designer session. So what will happen in this particular scenario, depending on the type of workflow, if it's a multi-material workflow, then a one job will be created. In this case, this is not a multi-material workflow that is already present in the session. And that's why we have now the formula field inside the name of the job. See, it wasn't present there before. Now when we have multiple materials, we have the formula variable that will be substituted using the formula for a particular material. So this is a convenient way for users to make multiple jobs at once and then mark those jobs according to the structure that they're studying. Okay, we can circle through these different materials that are present inside the job designer to make sure that those are the ones that we want to work with. The second step is to select a workflow. just as step number one, we click on the dropdown, click select workflows, and choose one of the workflows from our account collection. And here we go. This is one of the density of states that we just selected from our accounts workflow list. And the third step is to select the computational parameters for our job, or for multiple jobs. In this case, each of them will be created with these computational parameters. And this is a complex subject in and of itself, probably a subject to another discussion, a more detailed discussion, but there are things like time limit. So this is an absolute time limit. Your job is not going to run for longer than that. In some cases, we allow people to run jobs in the on saving resources in a restartable manner. So saving resources provide the way for users to cut costs. Usually it could be up to 5 times less expensive than the ordinary infrastructure. But at the same time, these jobs can be terminated. So the time limit will define how long each of the iterations, each of the attempts on running these jobs will be run. We can then select different cloud providers like Amazon Web Services or Microsoft Azure through this form. We can set up the computational queue parameters for debugging. For small calculations, we suggest that users use debug queues. For production type calculations, we suggest that they use ordinary, regular, or ordinary fast queues. And then there are a certain set of queues that support things like GPU resources, and they're also identified by the letter G in front of the Q name. And there is a set of advanced options specific to the simulation engines that we're using, like Quantum Espresso, for example. And there is a way to notify the user about events that happen inside the job. Now, once we have these 3 parameters set, we can click on the Save button at the top, and this will complete the creation of the job. Now, a few important notes. Workflows, we made it by design so that workflows cannot be modified during the job creation. And we did that on purpose to assert data consistency. If we were to modify the workflows right during the job creation, it would complicate the user interface in the first place and also compromise the data. So we could change the simulation engine, for example. If we could do that, then we cannot guarantee that we're actually dealing with the simulation engine that was designed in the original workflow. So users should modify the workflows first and then select this modified workflow during the job creation. The unit input preview button can still be edited directly. We left that as a backdoor, as an option for users to bypass these limitations, but we don't recommend that because this can indeed affect data consistency. And then multiple materials can be selected for either high throughput job creation, so we can create multiple jobs for each of the materials that we hold inside the session, or we can create a multi-material job, a single, for things like NEB calculations. It's still going to be a single job, but inside itself, it will include a reference to multiple structures. And jobs can also span other jobs and wait for their execution, but that's a topic for a separate discussion. So now, once we have created a simulation job, it shows under the list of jobs, and initially it has the status pre-submission, which is shown in the bright blue and letter P. So what we can do then is we can select the item and click on its dropdown in the list, and then click on Run to submit this job for execution. It will first transition into the status submitted and shown in darker blue. And after a little bit of time, we will see that it enters the active status shown in orange. And that's when we can come back and review the progress of the job. To do that, we would click on it, on its name in the list. And then we open the job viewer component. So here, besides the original 3 tabs for materials, workflows, and compute, we also have the tabs for results and files. That's where the results and the files produced in this calculation will be. And as you can see, the currently active sub-workflow and the currently active unit of the sub-workflow are highlighted in orange. And in gray are the ones that are yet to be started. So when we click on the unit name, we can see the standard output as posted to the web application in real time. And we can see the real-time chart of the convergence graph. Okay. As the units are progressing, the completed ones are shown in green. And at the end, when the calculation is entirely completed, all the units are finished, it is transitioned to the finished status shown with the screen icon and letter F. If we navigate back to this job, we can see the results that are arranged per each workflow unit. So pw.x has extracted these results. Right? The band structure, bands unit extracted the band structure plot. And if you navigate back to the top and click on the Files tab, we can see the files, we can preview them on the web, or we can download them to edit them locally. Okay, so that's how we run the calculations. That's how we use the materials and the workflow information inside the platform. This is all the content that I had for today. We have about 5 minutes left. Let's see if you have any questions or anybody wants to speak up and ask the question. If you do, please raise your hand, or alternatively, you can type a question in the Q&A session. Don't see any questions as of yet. I do hope it's clear how to use the functionality. If it's not, please let me know. Okay, no Q&A questions, no chat questions. Okay, it looks all right. Something is coming up. Let's see. Okay, Simon is asking, how would I integrate my external cluster, for example, Slurm? Okay, that's a great question. So obviously, this is an involved process to integrate an external and internal cluster. If we come back to the diagram that demonstrates the exabyte platform components, so an external cluster is what we depict here. So what we would have to do is to install parts of the exabyte open source infrastructure on that external cluster so that we can extract the information from it and then store it inside the database. And besides that, we will also have to incorporate, to be able to submit calculations to that external cluster, we'll also have to deploy some of the components that are not explicitly present here to be able to communicate with the front end and accept the simulation jobs. So we'll have to incorporate some parts of the messaging infrastructure to be able to get the information from the exabyte platform for the jobs that users are designing, and then translate this information to the native format of this high-performance computing systems. So if you use Slurm, we would be able to, through a plugin, incorporate this infrastructure and communicate directly with Slurm to submit those calculations. And then when the calculations are done, we'll use extractors to get the information from them and then post back to store it in the database. Okay, I do hope this is clear. Please let me know otherwise. That's a great question. Anybody else wants to ask a question? Looks like not. Okay, well, if you come up with anything in the future, please hit me up at timur@exabyte.io. You can also submit a support ticket through the platform if you're experiencing a particular problem. So let me come back to that part of the explanation. Support tickets usually are where do we have them? These components. Yeah, here at the bottom we have the support widget. So if you experience problems, something doesn't work, or you have a question about the documentation, please submit a support ticket. We usually reply within a couple of hours. Someone from our team will reach out. Next time, in a couple of weeks from now, we will speak about advanced topics. And if you have any particular recommendations you'd like to us to cover a particular logic, right, like communicating with the platform through RESTful API, please let me know. We want to hear back from you and understand what the most interesting topics. But usually we focus on migrating a set of scripts. For example, if you have quantum espresso input files and input files inside bash scripts, how to migrate this information and this logic to the Exabyte platform. That's what we will be discussing in 2 weeks from now. So with that, I'd like to thank everybody. If there are no other questions, thanks for your attention. Stay safe and see you in a couple of weeks.